Hello there, welcome to this video where we start to take a look at section D of part 1 of the first edition of Whitehead and Russell's Principia Mathematica. Section D is titled Logic of Relations, and on page 244 we read, "In the present section we shall be concerned with such of the general properties of relations as have no analogues in the theory of classes." So I'll be taking a look at chapters 30 to 34 in this video, and then chapters 35 to 38 in the next video. I've tended to cover previous sections in some detail so that whoever's watching these videos can get used to the style of Principia Mathematica, and I've tried to give sufficient explanation of the new concepts that Principia Mathematica makes use of. If you've got your head around these concepts so far and the way that Principia Mathematica works, then these things are generally much easier going forward. Nevertheless, I don't want this video to be too superficial. So I was still trying to explain things in sufficient detail, but many of the new concepts are often just special cases of previously introduced concepts, or are very closely related to them anyway. So if I do seem to cover a particular concept quite quickly, then it might be because I've already covered that concept in more detail in a more general form in a previous video. Therefore, it stands to reason that what I cover in any video of this series assumes that the contents of previous videos have been sufficiently well understood. These videos are not meant to be a substitute for you, as someone who wants to understand Principia Mathematica, doing much of the hard work for yourself. I aim to make the process of understanding Principia Mathematica easier, if I can, but no matter how hard I try, I can't make the process easy. Principia Mathematica is not easy to understand. These videos alone will almost certainly not be sufficient to develop a good level of understanding of the system of Principia Mathematica. So anyway, in this video, I'll be mostly concentrating on explaining the conceptual side of Principia Mathematica rather than looking at specific propositions and demonstrations. Now, of course, if there are any particularly interesting or useful propositions or demonstrations that are worth singling out and focusing on for a while, then I'll do so. However, many of the propositions and demonstrations are not of interest in and of themselves. They're really just setting things up for more substantial developments later. What's more interesting for the time being is the general trajectory and development of the system. The demonstrations generally don't present many difficulties. If you've understood the demonstrations up to this point, then going forward there's nothing really that you'll find to be too much of a problem. As mentioned in the previous video, at this point in Principia Mathematica, Whitehead and Russell are really just giving sketch proofs and may only indicate the main propositions which have been used in the demonstrations. It may sometimes be difficult and time-consuming to fill in the gaps that Whitehead and Russell have left. It isn't necessary to go through every single demonstration in detail. When reading Principia Mathematica, I personally will tend to just maybe choose a couple of demonstrations to work through in more detail so that I'm not reading completely passively. And it's good practice for me, but mostly henceforth I'm interested in the propositions and concepts introduced, not so much the pedantic details of the demonstrations. At this point in Principia Mathematica, I personally tend to be thinking more informally, and I think there's a reason why mathematicians tend to work their solutions to problems out in an informal way, at least initially. Informal and intuitive arguments, despite certain limitations, are much more natural and provide much more clarification than do formal arguments, typically. Of course, we do need to be able to reduce, at least in theory, any informal argument to a formal argument. Nevertheless, my opinion is that even though it's easy to follow the demonstrations of the propositions, it becomes increasingly difficult to figure out the demonstrations of propositions from scratch, if that's something that you want to do. And unless the previous propositions are well known and understood, then it's almost impossible to figure out demonstrations from scratch on your own. I'm certainly not at the level where I know by heart all of the propositions, and it would be interesting to know how Whitehead and Russell worked out the demonstrations and details of Principia Mathematica between themselves and how long it actually took them. Having said that, it's still worth trying to figure out some of the omitted demonstrations in more detail than what's given in Principia Mathematica, even if you don't do it entirely from scratch, but simply using the hints given by the authors. Okay, so let's have a look at Chapter 30, Descriptive Functions. The term descriptive function emphasizes the connection that that they have with descriptions. That is, a description exists in the sense of 14.02 when there is exactly one object that is denoted. The object denoted may be an individual, a class, a relation, and so on. Descriptive functions defined in 30.01, as shown, are effectively the kinds of functions that are common in mathematics. A function in mathematics, which is a special case of the more general concept of relation, associates with each of its arguments x a single value of the function f of x. On page 15 of the introduction we read, propositional functions are the fundamental kind of function from which the more usual kinds of functions such as sin x or log x or the father of x are derived. These derivative functions are called descriptive functions. On page 245 we see the functions hitherto considered have been propositional, and it goes on to say, but the ordinary functions of mathematics such as x squared, sin x, log x are not propositional. Functions of this kind always mean the term having such and such a relation to x. For this reason, they may be called descriptive functions because they describe a certain term by means of its relation to their argument. And Russell and Whitehead go on to explain further on page 245 that sin pi by 2 is a description of the number 1, namely 1 is described as the sine of pi by 2. But the proposition sin pi by 2 equals 1, or more precisely, the sine of pi by 2 is 1, is a substantial proposition and not a mere statement of identity, as is the proposition 1 equals 1. Russell goes into more detail with this idea in his Author of Waverley argument in his famous article titled On Denoting, and also in the introduction to Principia Mathematica. Then on page 33 we read, if R is any relation, we will speak of R primed y as the associated descriptive function, and instead of a variable descriptive function fy, we put R primed y, where the variable relation R takes the place of the variable function f. Note that whereas typically in mathematics we would write y equals sin x, in Principia Mathematica things are sometimes the other way round, and we'll often see y as a kind of independent variable and x as a kind of dependent variable. And to this effect on page 245 we read, we should write sin primed y in place of sin y, using sin to express the relation of x to y when x equals sin y. And I'll have a little bit more to say about this later in the video when we come to domains and codomains of relations. Descriptive functions are, as we see, simply special kinds of descriptions as introduced in number 14, where the propositional function denoted phi in definition 14.01 is of the form x has the relation r to y, or xry. We're not yet in a position to define the common mathematical functions such as x squared or sin x and so on, but we can be sure that they're in there. We just can't pick them out yet from amongst the whole collection of descriptive functions. That descriptive functions are a particular kind of description is clear from the definitions of definition 30.01, but is made even more clear from propositions 30.1 and 30.11. However, descriptive functions are derived from relations rather than general propositional functions, and this means that all of what applies to descriptions from number 14 applies to descriptive functions, but descriptive functions have their own specific properties that general descriptions do not have, and it's some of these properties which are presented in number 30. Of course, since descriptive functions are a kind of description, then they are incomplete symbols. That is, their use is defined, but the symbols have no meaning by themselves. Whitehead and Russell say on page 246 that definition 30.01 is more purely symbolic than other definitions, and go on to say that it would be perhaps more formally correct to write f of r primed y equals f of the x such that x are y, or even to include the scope of the description as well. A clue that we're dealing with a descriptive function is the inverted comma, for example, like the one in r primed y. These commas will appear all over the place when we come to domains, converse domains, unit classes, products and sums of classes, and so on, so keep your eye out for them. On page 32 of the introduction we read, the inverted comma may be read of, thus r primed y is read the R of y. For proposition 30.22, note that in the same way that we can't simply assert identity for a description with itself, since we also require that the x such that phi x exists in the sense of definition 14.02, and as we see in proposition 14.28, we can't simply assert that r primed y is equal to the x such that x r y. We require that r primed y exists, again in the sense of definition 14.02. In these propositions, it's usually quite easy to see that the propositions ought to be true, certainly in the case when we have that r primed y exists in the sense of 14.02. We have that r primed y exists only when there is exactly one object x for which x r y holds, which of course is typical of descriptions. If there is no such object, or if there is more than one such object, then we do not have that r primed y exists in the sense of 14.02. Of course, we may have that the same object x satisfies xry and xrz, where y and z are unequal objects. And this, of course, coincides with the modern notion of a function in mathematics, where a function can be one-to-one or many-to-one. General relations can also be one-to-many, but a one-to-many relation is not usually considered a function in modern mathematics unless a suitable restriction is applied to the relation. Many of the propositions in this chapter are exactly the kind of thing we would expect a suitably defined r primed y to behave like. For example, in proposition 30.34, we see that if two relations R and S are formally equivalent for all x, then this implies the equivalence between the propositions the x which has relation R to y exists and the x which has relation S to y exists. Of course, due to the formal equivalence of the relations R and S, the x which has relation R to y will be the same as the x which has relation S to y whenever they exist. Proposition 30.35 effectively confirms this. 30.42 is a proposition which can be compared to the notion of equality of functions in contemporary mathematics, where two functions are equal if and only if they agree on every value of the domain. So the truth of many of the propositions can be easily seen on an informal level. The demonstrations just show us on a more formal level that things work in the way that we want and expect them to. And the more we see on a formal level coinciding with what we expect on a less formal, more intuitive level, the more we see that the system is the kind of system that we want it to be. For example, 30.32 shows that the proposition that r primed y exists is equivalent to the proposition that r primed y has the relation R to y. And of course, this is entirely expected. If this were not the case, then it would potentially indicate a serious flaw in the definition of r primed y, as it would not seem to behave in the way that we would really like it to behave. The definitions and primitive ideas of Principia Mathematica are not random. They're meant to produce a system that aligns with our intuitive expectations in certain respects. That's not to suggest that there are no surprises in the system, things that we didn't anticipate and which may ultimately feel counterintuitive. To what extent Principia Mathematica succeeds in realizing a system that matches our intuitive expectations is, of course, quite subjective, and I won't get into that in this particular video. I do just want to go through the demonstration of 30.501 because I honestly found this a pain in the ass to figure out. Of course, it might just be me, but just on the off chance that anyone else has difficulties with it, what follows is my understanding of this particular proposition. Even though I'll go through this demonstration in some detail, there are still some things that I've necessarily left out, otherwise it just gets too unnecessarily pedantic. Often trying to add in every tiny little detail doesn't bring any further clarity, but often considerably diminishes clarity because it draws attention away from the more important aspects. You can add these extra little details in yourself if you want to, and this can certainly be worthwhile doing in the early stages of Principia Mathematica, or when you're trying to get used to the notation and so on, but it isn't worthwhile beyond a certain point. So this proposition makes use of definition 30.02 and the comments at the bottom of page 246, which elaborate how an expression such as r primed s primed y, that is, a descriptive function of a descriptive function, is to be interpreted. So let's have a look at the demonstration of this proposition. What I found difficult here was figuring out the right substitutions at each stage. The propositions that are demonstrated in Principia Mathematica are often forms, in a sense. So for a proposition of a certain form which has been demonstrated, then any other proposition that has the same form is an immediate consequence. And the problem is that sometimes it just isn't always obvious that a particular proposition is of a particular form. And just for clarification, I use the term immediate consequence here in the informal sense that Whitehead and Russell seem to be using the term on page 247, not in the precise sense that, say, Kurt Gödel uses the term immediate consequence in his On Formally Undecidable Propositions paper. Okay, so we start off with an application of proposition 14.1, which is shown on the screen, with the substitutions that are also shown on the screen now. And with these substitutions, 14.1 becomes as shown on the screen, which is the first line of the demonstration. Next, we have an application of proposition 14.122, again shown on the screen. And if we now consider the expression highlighted and use the substitutions which I've shown on the screen, then 14.122 becomes as shown, which of course gives the next line of the demonstration, where I'm also made use of definition 4.34. Next is a simple application of 4.3, just to reorder the factors. And now we have an application of 14.205, which is shown on the screen. Consider the expression which has been highlighted and make the substitutions which I've shown on the screen, in which case 14.205 becomes as shown, and which of course gives the next line of the demonstration. Now we make another application of 14.122 and we consider again the expression which has been highlighted, which I've rewritten using 4.3 as also shown on the screen. I'll make the various substitutions which I've shown, and in this case 14.122 becomes as shown on the screen, which gives the next line of the demonstration, in which I've also used definition 11.03 as well. And finally an application of 14.202, where we consider the expression which is highlighted, and I make the substitutions as shown, so that 14.202 becomes as shown, which gives the final line of the demonstration. And on the screen now I show the whole demonstration. And that's about all I want to say about this chapter. So let's take a look at some converse relations. Definition 31.01 tells us what a, but not necessarily the at this stage, converse relation of a relation is. That is, the relation that a relation Q must have to a second relation P for Q to be called a converse of P. We don't yet know that a given relation necessarily has a converse, nor do we know that if a relation has a converse, that this converse is unique. So we do need to have a little bit of patience. Definition 31.02 defines a relation P brev in terms of the relation P. And I hesitate at this stage to call P brev the converse of P from the outset, because this is not guaranteed by the definition alone. Of course, the definition is such that this will, or at least we hope it will, be the case. Nevertheless, a few propositions have to be proved before we get to that point. This definition, as with others which appear in Principia Mathematica, is, using Whitehead and Russell's language from page 246, a more purely symbolic definition, since relations, recall, are incomplete symbols. However, this definition stood out to me and was a definition that I spent a little bit of time experimenting with, and in particular I was interested to see what effect it would have if P brev was instead defined to be y hat x hat ypx, and the effect is that we would end up with x P brev y is equivalent to xpy, which is not a result that we want to have in general. Compare with proposition 31.11. This is a result of the convention stated on pages 211 and 212, and I won't go into the details here, but maybe try it out for yourself. But what this demonstrates to me is just how carefully things have had to be defined to make things work. As I mentioned a few minutes ago, the definitions and propositions of Principia Mathematica, they're not random. One faulty definition could be enough to throw everything out of whack. The system of Principia Mathematica is ultimately a failure, but it still leaves me in awe that such a rich system was ever created. I'm constantly impressed by how things tie together, and even after having read certain parts of Principia Mathematica dozens, if not hundreds of times, there are still things that I never really noticed before. Seemingly insignificant little details that seem almost irrelevant at first glance. And what I've come to realise is that there's barely a redundant word in Principia Mathematica. Almost every sentence seems to be necessary at some point. And it's not for no reason that, speaking about the system of Principia Mathematica, Imre Lakatos says in his article Foundations of Mathematics that the system of Principia Mathematica is one of the most complicated conceptual labyrinths a human mind ever invented. Anyway, Proposition 31.101 says that there is a unique converse of a relation. That is, there cannot be more than one relation which is related to R via the relation CNV, or at least all relations which have the relation CNV to P are equal. This does not in and of itself guarantee that the converse of a relation exists, simply that when it does exist, it must be unique. 31.111 shows that the relation defined in 31.02 and the relation P satisfy the relation CNV. This is a good sign because we do, after all, want P brev to be the converse of P. Note that the verification that P brev is the converse of P comes in Proposition 31.12. We still don't have assurance that every relation P has a converse, just that if P does have a converse, then it must be the relation defined in 31.02, but then at last, in 31.13, every relation has a converse. And notice in 31.13 we see CNV primed P is a descriptive function which is indicated by the prime. Thus, CNV primed P may be read the object which has relation CNV to P, or more informally, the converse of P. Of course, a relation may be self-converse. For example, 31.21 and 31.22 show that the null relation and universal relation are both equal to their respective converse, that is, their self-converse relations. These are but two examples and does not in any way exclude the possibility of other self-converse relations. On page 251 we read when R equals R brev, or we might even say now when R equals the converse of R is called a symmetrical relation. Otherwise it's called not symmetrical. When R is incompatible with the converse of R is called asymmetrical. We also see on pages 33 to 34 of the introduction, a relation is called symmetrical if R is equal to the converse of R, i.e., if it holds between y and x whenever it holds between x and y, and therefore vice versa. A relation is called symmetrical when it is incompatible with its converse, i.e. when the logical product of the relations R and the converse of R is equal to the null relation, or what is equivalent, xry formally implies not yrx. Incompatible relations are not relations of different types, since the logical product of two relations of different types would be meaningless. The converse relation of the converse relation is the original relation. This is proposition 31.33. The symbol CNV primed P will have to be interpreted in the way indicated in the notes for definition 30.02. Also see the demonstration of proposition 30.501, which I elaborated on previously in this video, which might give some clues how to interpret this descriptive function of a descriptive function. There appears to be a typographical error in the references to propositions used in the demonstration to proposition 31.14. The second mention of proposition 21.33 should be 23.33. And there's also a couple of typographical errors in the demonstration of 31.16. Both mentions of proposition 21.35 should be 23.35. And finally, this is an observation that doesn't really affect anything, but an observation nevertheless. there's some strange numbering of propositions where we jump from proposition 31.24 to proposition 31.32. This maybe suggests to me that there was some other propositions in between these two at one point, maybe propositions 31.3 and 31.31, for example, but maybe they were removed because they were ultimately deemed unnecessary, but to change the numberings of the propositions which remained would have involved too much work, going through Principia Mathematica to change every individual reference. Easier just to leave the weird numbering instead. So anyway, let's leave this chapter and move on to the next one. 32. Referents and relata of a given term with respect to a given relation. Now there's nothing particularly difficult about this chapter. There's a few new definitions which I'll try to explain as well as I can in this video, but the demonstrations of propositions are typically fairly straightforward and are often just verifying the uniqueness of certain classes or relations, and really just showing that the definitions work in the way that they're intended to work. For a given relation R and for a given Y, there may be several x's which have the relation R to Y. These x's which have the relation R to Y are called the referents of Y. Moreover, these x's can be considered as forming a class called, funnily enough, the class of referents of Y. And this class can be denoted x hat xry for a given Y. There's also a relation which the class of reference of Y has to Y, and this is denoted R with an arrow pointing to the right above it. 32.01 defines the relation between classes and objects where a class alpha has the relation R right arrow to Y, whenever alpha is equal to the class of reference of Y. And now on the other hand, for a given x, there may be several y's to which x has the relation R. These y's to which x has the relation R are called the relata of x. Again, these y's can be considered as forming a class called, would you believe, the class of relata of x, denoted y hat xry. And also again, there's a relation which this class of relata of x has to x, and this is denoted R with an arrow above it pointing to the left. 32.02 defines the relation between classes and objects where beta has the relation R left arrow to x whenever beta is equal to the class of relata of x. There are thus two further relations that can be considered. One, the relation of R right arrow to R, and two, the relation R left arrow to R. The former is denoted SG and the latter is denoted GS. And 32.03 defines the relation SG and 32.04 defines the relation GS. We don't assume from the outset that there is only a single unique class of reference or relata, but of course if the definitions are satisfactory, then it will be possible to show the uniqueness of these classes, and that's what we see in propositions 32.1 and 32.101, which, assuming that there are such classes which may be equal to the null class, then they must be unique. And then by 32.13 and 32.131, these classes must be equal to R right arrow primed Y and R left arrow primed X respectively. By 32.12 and 32.121, both R right arrow primed Y and R left arrow primed X exist as descriptions, but not necessarily in the sense of classes having at least one member. That is, there is always a class that is the class of reference of Y and a class which is the class of relata of X. Note that R right arrow primed Y and R left arrow primed X are descriptions, indeed descriptive functions, as indicated by the inverted comma. Considering the comment on page 257, it would seem that the class of reference of Y, R right arrow primed Y, may be the null class, since the null class is still a class. And in this case we have that R right arrow primed Y exists in the sense of 14.02, but not exists in the sense of chapter 24, the latter meaning that R right arrow primed Y is a class with at least one member. And similar comments can also be made for the class of relata of X, R left arrow primed X. So let's take a look at proposition 32.132. R right arrow primed Y is a description, and by definition 30.01 this is equal to the alpha which has relation r right arrow to y. So by an application of 20.57, and okay, it doesn't really have any real bearing on the demonstration, but I may as well point it out anyway. Note that the form of 20.57 used in the demonstration of this proposition is of a slightly different form to the form given in the statements of 20.57 in Principia Mathematica. So by this application of 20.57, with the substitutions that I've shown on the screen, then 20.57 becomes the assertion as shown. But we also have proposition 32.13, and therefore, by an application of 1.1 and 32.1, the result follows. It can help sometimes to understand some of the concepts involved a bit better, to think about how some of the propositions may be understood using less formal reasoning rather than the purely symbolic demonstrations. This is not to suggest that the formal demonstrations can be substituted for informal demonstrations, but thinking through the concepts informally can help, or at least it helped me, to visualize things a bit better. Note that sometimes informal reasoning will be longer than the formal demonstrations, but the point of informal intuitive justifications is not necessarily brevity or even to prove the propositions, just to help visualize them and familiarize yourself a bit better with them. So for example, proposition 32.24. GS primed R is R left arrow, which by definition 32.01 is as shown on the screen. And similarly, SG primed R brev is R brev right arrow, which is shown on the screen, which is by definition of converse 31.01 equal to as shown, which is equal to R right arrow. And hence, GS primed R is equal to SG primed R brev. Or, as a second example, 32.3, SG primed of the logical product of the relations R and S is the object which has relation SG to the relation which is the logical product of R and S. By uniqueness, this must be the relation of the logical product of R and S right arrow. So SG primed R logical product S must be equal to the logical product of R and S right arrow. So SG primed of the logical product of R and S primed Y must be equal to the logical product of R and S right arrow primed Y, which must be equal to the object which has relation the logical product of R and S right arrow to Y, and thus must be equal to the class of reference of Y with respect to the relation the logical product of R and S. The class of reference is the class of those x's which have relation the logical product of R and S to Y. And we can see on a diagram that this is the logical product of the class of x's which have relation R to Y and the class of x's which have relation S to Y. That is the logical product of the class of reference of Y with respect to R and the class of reference of Y with respect to S, which is what the proposition states. Notice that the informal reasoning often more or less follows the formal reasoning in a certain sense. This wasn't intentional as I was thinking informally through these propositions, but it can be seen from this how informal reasoning may stimulate ideas about how the informal reasoning may proceed. If you are having trouble coming up with formal demonstrations for the propositions, then try working more informally. Informal proofs are in some ways easier to come up with in the first instance than going straight for a purely formal demonstration, and once an informal argument has been found, then it may suggest a formal reduction. And this kind of informal reasoning can help in the chapters which follow on domains and converse domains, which can be treated in quite a visual sense. And this informal reasoning can sometimes shed more light on a proposition than the formal demonstrations, though of course the formal demonstration is what we ultimately require here. But let's face it, mathematics as it's done in practice uses informal reasoning the overwhelming majority of the time, so we may as well make use of it here as well. And now just one final point here. There appears to be a minor typographical error in the comment following the statement of 32.35. the proposition 32.2 cited should be proposition 32.3. Okay, so let's move on to the next chapter. The relations domain, converse domain, and field are defined in 33.01, 33.02, and 33.03 respectively. We read on page 260, if R is any relation, the domain of R, which we denote d' R, is the class of terms which have the relation R to something or other. The converse domain is the class of terms to which something or other has the relation R, and the field is the sum, that is, the logical sum, of the domain and the converse domain. Note that the field is only significant when R is a homogeneous relation. A homogeneous relation is described on page 256 as being a relation whose referents and relata are of the same type. On page 261 we read that if the relation R is not homogeneous, the field is meaningless. As can be seen, d'R, C'R, etc. are descriptive functions as indicated by the inverted commas. So I'll just pick out a few propositions which are noteworthy here. 33.18, if the domain and converse domain of a relation exactly coincide, then they're both equal to the field of R. 33.2, the converse domain of R is equal to the domain of the converse relation of R. 33.21, the domain of R is equal to the converse domain of the converse relation of R. 33.24, the domain of a relation R has at least one member is equivalent to the converse domain of the relation R has at least one member, which is also equivalent to the field of the relation R having at least one member, which is equivalent to there being at least one pair, x and y, which satisfy the relation xRy. 33.32, note that the logical product of two relations may be equal to the null relation, but this does not in any way mean that the logical product of their respective domains must be equal to the null class. It may be that x is a member of the domain of R and a member of the domain of S, and hence a member of the logical product of the two domains, but we have xRy and xSz, where y and z are unequal. 33.432, if R'y exists for all y, then for every y of a given type, there is an x for which xRy is true. So the converse domain of R is equal to the universal class. Many of the propositions of this chapter are fairly mundane, so I won't go into detail with them here. However, I just want to relate some of the concepts of this chapter with descriptive functions. On page 33 we read, every descriptive function has what we call a domain of definition or a domain of existence, which may be thus defined. If the function in question is R'y, its domain of definition or existence will be the class of those arguments y for which we have R'y exists, i.e. for which the x such that xRy exists, i.e. for which there is one x and no more having the relation R to y. On page 261 we read, consider first the sort of relation that gives rise to a descriptive function R'y. For this we require that R'y should exist whenever there is anything having the relation R to y, i.e. that there should never be more than one term having the relation R to a given term y. In this case, the values of y for which R'y exists will constitute the converse domain of R, and the values which R'y assumes for various values of y will constitute the domain of R. Thus the converse domain is the class of possible arguments for the descriptive function R'y, and the domain is the class of all values of the function. So I just want to draw attention to something here. The word domain is seen to be used in Principia Mathematica with a slightly different meaning to what it's taken to have in certain contexts of contemporary mathematics. In modern mathematics, the domain of a function would be something like the set of possible arguments of a function. However, as we've just seen in the passage just quoted from page 261, the domain of the descriptive function R'y is the class of all values of the function, not the class of all possible arguments. And hopefully to clarify further how a descriptive function is to be interpreted, in a passage which I've already mentioned previously in this video on page 245 we read, in our notation, r primed y takes the place of what would commonly be fy, this latter notation being reserved for propositional functions. We should write sine primed y in place of sine y, using sine to express the relation of x to y, where x equals sine y. This is a good example of how when reading historical works in mathematics, you often have to be prepared to put aside your understanding of how terms are used in modern mathematics. Even works from 100 or so years ago can be quite a challenge to read. How Whitehead and Russell define domains and converse domains is not in any way wrong. It's just particular to the system of Principia Mathematica and makes sense in that context. Bear in mind that the system of Principia Mathematica is only being investigated as a potential theoretical foundation and in a certain sense a model for certain parts of mathematics, and is not mathematics itself. So I'm not going to say anything further about number 34, the relative product of two relations, in this video. This chapter is fairly self-explanatory and there isn't anything particularly difficult contained therein, at least from what I can see. So that brings us to the end of this video. I do have another video planned for this series which will cover the remaining chapters of section D of part 1, and I've also got another video lined up with some miscellaneous aspects of Principia Mathematica. I don't know how many more videos I'm going to make in this series of videos. The next two videos might be the last ones that I make, at least for a while. I think many of the concepts essential to understanding Principia Mathematica have already been introduced by the end of section D, and I'm keen to look at some other things, possibly make some videos on other works, but there's also some works relating to Principia Mathematica by other authors that I would like to take a look at if I have time to do so. I probably will pick back up with Principia Mathematica at some point, but I don't know, maybe not for a while. It depends how I feel. Anyway, thank you for watching this video to the end. Please let me know what you think in the comments section if there's anything that you'd like to add. Please hit the subscribe button, give this video a like, and I will see you in the next video. Ciao for now.